Hi everyone, in this video we're going to be talking about graphs of equations in two variables and their intercepts, and then we're actually going to split this section into two parts. In the next video we'll talk about symmetry. So let's jump right into this. So we're going to do some of these objectives here and then the rest in the next video. So we're going to graph equations by plotting points. We're going to find intercepts from a graph, and then also we're going to find intercepts from an equation. And then in the next video, we'll do the other two objectives. So to graph equations by plotting points, and this is for an equation in two variables. Okay, so normally we use the letters x and y, but it doesn't have to be x and y. But most of the time, those two variables are going to be the letters x and y. So it's basically just a statement. So the equation is a statement involving the two variables x and y, where both sides of the equation are equal. So you'll see some equal sign, and then some x's and y's, some expressions. So the expressions are called the sides of the equation. Okay. If you don't have an equal sign, then it's just an expression. But the minute you put an equal sign, then it becomes an equation. Just a subtle thing there to mention. And then any values of x and y that result in a true statement are said to satisfy the equation. So this is just some background, some terminology for us. Some equation, expressions, sides, satisfying an equation. Those are things that we would just want to know what that means. And then the graph of an equation in two variables, x and y, it's just all the points. So it's the set of all the points in the xy plane, which we talked about in the last video. That's the Cartesian coordinate system or rectangular coordinate system, whose coordinates satisfy the equation. So pretty much it's all the points x comma y. Then when you plug them into the equation, the left side of the equation equals the right side. Alright, so here's our first example. Determining whether a point is on the graph of an equation or not. So determine whether the points given here, a and b, are going to be on the graph of this equation. So notice we don't have the graph. We could draw it, but we don't really have to. We could just plug in. We're going to just do this algebraically. So notice every time when you are given an ordered pair, the first number is always x, the second number is always y. So all you have to do here to figure out if this point is on the graph of this equation is to plug the numbers in for x and y. Okay, so where there's an x, we're going to put a 3. Where there's a y, we're going to put a 2. And then what you want to do is you want to use parentheses. I don't have them here, but let me just add them. You always want to put parentheses when you're plugging in, because it makes a big difference, especially if you have negatives. You don't want to lose track of your negative signs. So exactly where there's an x, I'm going to move up here. Let me go to yellow so you can see it. Right where there was an x, I'm replacing that with what x is, it's 3. And right where there's a y, I'm replacing that with 2. So notice that this doesn't equal 9 like the original equation says. So this point 3, negative 2 would not be on the graph of this equation if we were to plot it. Okay, so it doesn't satisfy the equation, and in other words. So checking the next point, x is 2, y is negative 3, plugging in. Notice this time the parentheses are there, especially in the case where there's a negative, because we end up getting negative times a negative is positive. So this is 6 plus 3, which is 9. So this does satisfy the equation. And so if we were to graph that original equation, this point would be on the graph, because when we plugged it in, the equal sign was still valid. We didn't have to cross it out. All right, next one, graph this equation. So the last one, we were just checking are the points going to be on the graph. Now we're actually going to draw the graph. So the graph consists of all the xy points that satisfy the equation. There are infinitely many. So all here is infinity. It's infinitely many x's and y that satisfy this equation. X could be 0, and then y would be 3, x could be 1, and so on. And so we could plug in so many points. But we don't have to plug in a ton of points, just a few, and then connect them to draw the graph. So to locate some of these points, assign some numbers to x and find y. In another example that we're going to do later, we're going to plug in for y and solve for x. But this one, it's easier to plug in for x because notice y is explicitly solved for, it's by itself. So in that case, we just find numbers for x, plug them in here, and then solve for y. Okay, so we can pick any numbers we want. It's usually good to pick some positive and some negative numbers, and then 0 as well. So I'm just going to pick these 5. So these are all your these are choices. They can be anything you want, but you just choose these numbers. Okay, so I'm going to choose that x is -2. When I plug that into the equation, notice that it equals 9, so y equals 9. And then if I plot this as a point, this is x, and when x is -2, then this is y. Y is 9. And then I do that for some more values, and you can pick anything you want once again, but I just pick some negative, so I pick some negative numbers, 0, some positive numbers, plug them each in, and then I get these corresponding 5 points, and then I plot those points. Okay, so notice I have the points plotted, and if you plot enough points, you're going to get the graph and the shape pretty clearly drawn out for you. The only way to connect these is to form a straight line. Okay, and then this right here is, and you'll recognize this more you work on these problems, the equation of a line. So in case you didn't know that right away, and that's perfectly fine, like let's say you had no clue that this was going to be a line, by plotting these 5 points, it's pretty clear that the only way to connect them is to draw a straight line. Okay, so when in doubt, this is what I like to tell people, because it helps, especially when we start graphing some more complicated functions and graphs. When in doubt, just plot lots of points. So plot lots of points, and if you know it's going to be a line, think about it, you really only need 2 points, because if I know it's a line, 2 points, connect them, draw the line. But if I don't know it's going to be a line, or I don't know what shape it's going to be, because sometimes it's a different shape, plot lots of points. If you don't know the shape of the graph, know the shape of the graph. And then this is going to get a little easier the more you work on these problems, because you'll recognize just from looking at the equations what the shape is going to be. So like I said, this one, just by looking, I can tell it's going to be a line. I'll give you a hint so you know why I know, and you might already know this. It's because this is considered linear when this is an invisible power of 1, and so is this. This is a linear equation, which is going to be a line. In the future, we'll learn things like, actually we'll probably look at some of these today, but this is a parabola when you graph it. Here's another example. This one here would be like a river type shape when you draw it. So there's all kinds of shapes that we can get from graphing. Alright, so let's try this one. Oh, and I kind of just mentioned it. So notice what we have, y equals 1/2 x squared. I just mentioned what the shape of this would be, but we'll go ahead and draw this out. Okay, so we create an xy table, and so you get to just choose. You choose your x numbers. They can be anything you want. I just happen to choose these same 5 numbers from the last example, but you can pick -30 or -1.5, but these are the ones that we're going to pick for x. You plug them in for y. So once you choose them, one at a time, you plug them in, and always use parentheses. Okay, I want to emphasize this. Use parentheses when you plug in. So think of like erasing the x and putting this number in its place inside parentheses. Why I'm emphasizing this is because I'll show you really quick off to the side here. So I'll just say that this is a note. If I didn't put parentheses, -2 squared is not the same as quantity -2 squared. Okay, on the right side, this is saying that I have -2 quantity times itself, because anything squared is times itself. And -2 times -2 is +4. But on the left side, there's no parentheses holding that negative sign with the 2. So really, the square is just going on, the second power is really only going on the 2. So this is saying 2 times 2 with the negative way out to the front. And so that's 4, and then that negative that was out front stays there. And so these are not the same. So my reason for showing you this note is because it's important when you're plugging in numbers into equations to put parentheses. It's not going to make a difference when you do it with positive numbers, but it's just a good habit to do it all the time so that you don't mess up when it does matter, like with negatives. Okay, so this one became 4, half of 4. 1/2 times 4 is 2. And so our point is x is -2 when y is 2. And we just do that for other numbers. 0, 0 is on the graph, 2, 2 is on the graph, and so we're going to plot these 5 points. Okay, so here are the 5 points we got. 0, 0, 1, 1/2, 2, 2, and then -1, 1/2, and -2, 2. So notice if you have tick marks, like let's say you're using graph paper, there's no half on your graph paper. So you just want to draw to your best of your ability, like halfway up this tick mark. So if this is 1, then 1/2 is halfway up there. Okay, and this is a parabola shape. So if we only had those 5 points and we didn't have the blue connecting curve, we could still draw that blue curve, because when we have those 5 points, we would say, okay, there's my 5 points. The only way to connect these is to go like this, draw a smooth curve. Whenever you draw your graphs, make them smooth. Don't do anything like, let me show you a mistake. So let's say, because I'm trying to emphasize that this is a smooth curve. I wouldn't do this. So this is wrong. I wouldn't do this. I wouldn't say, okay, there's a point there, so there's that, and then I'm going to go here, and there, and there. Like, see how I kind of just like made some jagged marks here? You wouldn't do that. You want to make it smooth when you draw your graph, and then that's going to be the graph of your equation. Okay, so we have what's called a parabola on this one. It's a parabola shape. Okay, so now we are ready to talk about intercepts. So intercepts are points on your graph, but they're very specific points. They're points where your graph either crosses or touches the coordinate axes. So we talked about this in the last video, but this is your XY axis. So your coordinate axes are just the terms for your x-axis and y-axis. Okay, creating your XY plane. That's what coordinate axes means. So if you didn't know that term, it just means your x-axis and y-axis. Where you touch or cross these axes, we call those points intercepts. Like when you intercept something, you meet it somewhere in the process. So in this case, we're meeting the point on the axis. Okay, so the x-coordinate, where your graph touches or crosses the x-axis, is, hopefully intuitively this makes sense, the x-intercept. And very similarly, the y-coordinate, where your graph touches or crosses the y-axis, is your y-intercept. And some graphs have multiple x and y intercepts. So for this, for a graph to be complete, all its intercepts must be displayed. So it's a really good habit to get into to plot the intercepts. So in this case, there's no numbers here, but notice that the points are marked. So where this touches the x-axis and where it crosses the x-axis, those points are plotted. Because there's infinity points on this graph. I want to make that point very clear really quick. So there's a point here, there's a point here, there's a point here, and so on. There's infinite amount of points on this graph. But what you want to do is you want to get into a habit of plotting at least the intercepts. You can plot more, you can plot all of these, but if you have at least the intercepts, then it makes the graph more clear to see. And usually the intercepts are important because they represent certain things, especially when we're doing like application problems, like real life problems with the graphs. Okay, so let's try this example, finding the intercepts from a graph. So find the intercepts, what are the x and what are the y intercepts. So this one, we're just looking. In the future example, we're going to solve for them algebraically. But here is the x-axis, the horizontal axis, and here's 2 points on the x-axis that our graph goes through or touches, is both intercepts. And so we just label those. So we have two x-intercepts, and then, so I'm going to write here that there's two of these, and then down here we're touching the y-axis, the graph goes through it, and so there's one y-intercept. So there's a total of 3 intercepts on this graph. Okay, and so there are these 3 points. These are both x-intercepts, and then this one over here is the y-intercept. And what you can do, sometimes it just honestly sort of depends on the book or your preference, but sometimes they're labeled as points, sometimes they're just numbers. I personally like to label them like this as points, but the x-intercepts, you could just say that it's 3 and -4, the x values. And then the y-intercept you could say is just -3, the y value. But like I just said, I personally choose this one because it's very clear that it's a point on a graph when I have x and y together. Okay, so what we're going to do in the next example, and I just want to mention it here so you see where we're going with this, we're going to solve for intercepts. We won't look at the graph, we'll solve algebraically. Notice with the x-intercept, what's true? What's true for both of these is that y is 0 for both x-intercepts. And think about why that's the case. Because anywhere on this x-axis, you're at a y value of 0. You never went up, you never went down from the origin, you only went left and right. So every single x-intercept, y is always 0 every time. And then what's also true, if you look over here at the y-intercept, x is 0. So every time you're finding y-intercepts, like you have right here, you're on the y-axis, and you never moved left or right from the origin, you only went up and down. So since you never moved left and right, your x stayed at 0. So for y-intercepts, x is always 0. So we'll write that down. Okay, so right here. So we have that for x-intercepts, if there are any, because some graphs don't have any, but if there are any, y is 0. You plug in 0 for y, and then you solve for x. Very much the same process for the y-intercept. For the y-intercepts, if there are any, because sometimes there's none, you let x equal 0, and you solve for y. So that's the process. Let y equal 0, solve for x, that gives you the x-intercept. Let x equal 0, solve for y, that gives you the y-intercept. So let's try it. Find the x and y intercepts of this graph, and then let's graph it by plotting those points. Okay, so do these one at a time. We'll start with the x-intercepts. So if I am asking to find the x-intercepts, if there are any, I have to let y equal 0. So all I do is I go to my equation, and if it's not clear, hopefully it is, but let me just make it very, very clear. The original equation was y equals x squared minus 9. All we did here was just move the y and the equal sign to the right side. So that's the same original equation. And where there was a y, we just put a 0. And then we solve. Okay, so you solve this equation for x. And you can do this two ways. So this is one way of factoring. So this might be familiar. Let me remind you about factoring. The other way is to solve using the square root property. So I'll say or. You could say x squared equals 9 if you add 9 to both sides. So this is or, either way. So if you add 9 to both sides, you can also solve this. And so let's go back and forth for the factoring. If you FOIL this out, hopefully these terms sound familiar. If you FOIL this back out, so first times first, outer times outer, inner times inner, last times last. If you FOIL this out, first times first, outer times outer, inner times inner, last times last, you will get exactly where you just came from, x squared minus 9. Okay, and then whenever you factor and the product is 0, so let me get rid of some stuff here, clear this up. So if the whole point of factoring is to be able to go to this next step right here, anytime you factor and the product is 0, the answer is 0, then either the first the first factor equaled 0 or the second factor equaled 0. And that's from what's called the zero product property. So once you factor, you go directly into this next step where you say the first factor equals 0 or the second factor equals 0. And so in our case, x is 3 or negative 3. Back to my other option over here, if I solved for x this way, I would take the square root of both sides. But anytime you physically add the square root symbol into a problem, you actually need to put a plus and minus. So if you take the square root of an equation like this, if I put a plus and minus, the left side is x, and the right side is square root of 9, but plus and minus. So plus and minus 3. Notice it's the same answers we got right here. Okay, and then over here, the square root undoes the square. You can think of it like this, like undoing itself. Okay, and then before I move on, just a quick side note, because you might wonder how did we factor this, but we're not going to really get into that on this one. I just want to remind you, in case you've seen this before, that this x squared minus 9 was set up like the difference of squares, if you've heard that before, which factors as a minus b times a plus b. So that's where we got the x minus 3, x plus 3 from. Okay, so that was just a quick note on the factoring that we did. Okay, so far we have two solutions, which are our x-intercepts. So as points, that would be 3, 0 and negative 3, 0. So those are our x-intercepts. And then our y-intercepts, very much the same process, but now you switch what you let be 0. We let x equal 0 this time. So from our original equation, just plug in a 0 right where there's an x. And this one's pretty easy. This one's really quick. Y equals negative 9. So our y-intercept is going to be 0, negative 9. And then we'll plot those points along with a few more points. So we only found 3 points from our work. We found negative 3, 0 and 3, 0, these x-intercepts. And then we found 0, negative 9. If I didn't know that this was going to be a parabola, then I wouldn't quite know how to connect these points. I might draw something like this. I might say, oh, this looks like this. So what I want to do, if I'm unsure of the shape, I want to plot more points. And so what we have here is a table with just a few more x values. So again, we just choose some x numbers here, and then we plug them into our equation. So negative 4 squared would be 16. 16 minus 9 is 7, and so on. And we plot more points, and then if we plot more points, we can connect these. And then now it's a little bit more clear that when I connect them, let me do my best to do a smooth curve here, that this is a parabola. Okay, and it goes, technically keeps going up. Another way to think about this is that x squared is always going to be 0 or more. Anytime you square something negative, it's 0 or positive. And so this is the lowest point on the graph. So all of our other points are going to be higher, which they were. In the future, just so you know, or maybe this sounds familiar because you've learned it in the past, but we'll learn about this later. This is called the vertex, this point here. Okay, so that is it for this first half of the video. And then the next half of the video, we're going to, or in the next video, the next half of this section, we're going to learn about symmetry of these graphs. Because this graph right here actually has symmetry. If you put a mirror on the y-axis, you could actually draw this graph in half the amount of points, because you would just flip it over and plot the other points. So we'll do that in the next video. Thanks for watching.